So I've got a PowerPoint for our April 20th class. I think I'll probably do multiple parts because I won't want individual ones to get too long. But the section we're going to talk about is a topic that you've heard before in general chemistry, the topic of colligative properties. In a PChem class, we're interested in the thermodynamic driving force for these properties, and you'll see that in some derivations, but we'll also see it in some real-life applications. And I'll give some problems at the end for you to practice these ideas on. So we're in a chapter on solutions, and so colligative properties are going to essentially focus on what effect the solute has on the properties of the solvent. And the way that it's framed here is solutes have the effect of changing the properties of the solvent, and we're going to be interested in the thermodynamic driving force. And as I kind of cheekily say here, the driving force for practically anything we do in chemistry is the Gibbs energy. How is introducing a solute into the solution going to affect the Gibbs energy? Well, we're going to end up deriving some equations that make three assumptions. The first one is that the solutions we're going to talk about are, quote, ideal dilute. Those are the ones that may not be ideal at all concentrations, but they're going to be ideal dilute in the range that we're talking about. So if you have a solute that has maybe less than a tenth of a mole per mole added to the solvent, you're going to obey Raoult's law for the solvent's vapor pressure, and you would probably obey Henry's law for the solute. Now, in this case, though, we're going to specifically mention non-volatile solutes. So that really takes the kind of the Henry's law consideration out of it for now. But thinking of gen chem experiments where maybe you took something like a salt, or maybe I remember doing naphthalene dissolved in cyclobenzene or cyclohexane for doing a freezing point depression type of thing. But we're going to consider a non-volatile solute for our derivations. And then finally, for now, we're going to view the solute as a non-electrolyte. Chapter 7, we'll get into solutions when you have ionic solutes. But for now, we're just going to do non-electrolytes. Well, I mentioned Raoult's law, so that's the place we're going to start for right here. Basically, this expression says that the vapor pressure of the solvent is going to be proportional to its concentration, or its mole fraction. So that mole fraction term is multiplied times the pure vapor pressure. So the vapor pressure ultimately is going to be lowered, and this derivation does a little bit of rearranging, and it expresses the lowering of the vapor pressure in terms of how much solute gets added. Now this chi2 term, this is essentially a concentration unit, right? The effect of the solute is just dependent on the number of solute particles. It doesn't have anything to do with how big they are, or their molar mass, or other properties of a solute that you might think would be important. It only depends on how much. This is what binds colligative properties together. It only depends on how much in terms of the number of particles you've added to your solution. Now, because we've done a lot in recent days in mentioning intermolecular forces, especially when we defined what an ideal solution was, you might be tempted to think that intermolecular forces are going to have something to do with lowering the vapor pressure of the solvent. And maybe your Gen Chem professor even mentioned that, somehow implying that the solvent and the solute interactions are sort of keeping the solute molecules from evaporating. But of course that can't be right. It can't be right because even ideal solutions show vapor pressure lowering. Remember what the definition is? It's the intermolecular forces of the solute and solvent are basically the same as the average of the individual intermolecular forces. So it can't be really an enthalpy argument. Really, that has to do with binding. Vapor pressure lowering can't be dependent on enthalpy. And as I say here, if you think entropy has something to do with it, well, then you've been paying attention. Because we know that if Gibbs energy is the driving force and enthalpy is not the reason, it's got to be entropy. Now, in general, again, we're talking about vapor pressure. In general, the entropy of the gaseous state is going to be greater than the entropy of the liquid state. And so you might say, oh, well, that's obviously the driving force. But you have to keep in mind, it's a little bit more nuanced than that. As we mentioned earlier in section 6.3, mixing itself causes an entropy increase. So if you're talking about a solvent evaporating from solution, you might think, oh, wait a minute, the fact that this is a solution means there's some disorder in the liquid. There's going to be less of a driving force, a smaller entropy increase when that solvent molecule evaporates. So this really ends up being the driving force for the lower vapor pressure. There's a lot of disorder in the solution, and even though going into the gas phase is a more disordered state than being in the liquid, the difference is less for the solvent molecule if it's leaving a solution rather than the pure solvent. Let's take a look at another application of colligative properties, and that is boiling point elevation. The definition, of course, of the boiling point is the temperature when the vapor pressure of the solvent is equal to the external pressure. So hopefully you can see why there's a connection to the earlier topic, vapor pressure. As we just discussed, the solute lowers the vapor pressure of the solvent, and by definition, that's going to raise the boiling point, because what was the temperature and pressure at which something boiled, that's going to lower the vapor pressure, and so you're going to have to go to a higher temperature to get to that point. Remember, thermodynamically, it's the change in the chemical potential. The chemical potential of the pure liquid has a new term now that's dependent on the mole fraction of the solvent. Because that value is going to be less than 1, that's going to add a negative value, and so the chemical potential of the solvent while it's in solution is going to be less than it was before. That's what this graph shows you here. In the dashed line, you're seeing the chemical potential of the solvent while it's in a solution compared to the value of the pure solvent line. And it's that intersection, it's a little hard to see on this graph, but if you take a look at your book, it's in there. So we see the intersection of the vapor line, which of course is going to be pure solvent because we define this as a non-volatile solute. The chemical potential of the pure vapor isn't changing, but the intersection with the liquid phase does change. And you see that the intersection for the solution, which is the dashed line, indicated by TB prime, is a little bit to the right than the intersection with the solid line, which is the boiling point of the pure solvent. So you can see you're getting a boiling point elevation due to the lowering of the chemical potential of the solution. So I had mentioned that this is a PChem version of something you've seen before, and here's where I really show this for you. It's not, of course, that I'm going to ask you to memorize a derivation, but I want you to kind of see the origin of where some things that were just sort of handed to you when you first saw chemistry, where they really come from. So here's a quantitative treatment of boiling point, and as I say more specifically, the route to an expression for concentration's effect on boiling point. So we just established the idea based on entropy and chemical potential why the boiling point changes. Here's where the degree of how far that dashed line gets moved from the solid line comes from. So something you've seen before is the idea that chemical potentials of things in equilibrium are equal to each other. So that's at the first half of this. We see that the chemical potential of the solvent in the gas phase has to be equal to the chemical potential of the solvent in the liquid phase as long as the system's at equilibrium. Now the solvent's chemical potential can be expressed, and we've seen this before, as the pure chemical potential plus a correction term depending on its concentration. So what that ends up meaning is you could rearrange this to show that the difference of the chemical potential of the solvent is going to be the difference between the chemical potential in the gas phase and the pure chemical potential. So as we said, sort of that correction term is the source of the change in chemical potential, or again, how far that dashed line on the previous slide moves from the solid line. Now, if you do this for 1 mole, it becomes a molar difference in chemical potential, or you could call it the molar change in the Gibbs free energy. of the process of vaporization. And so by combining this idea with the equation above, you can get that. Now, this equation may not ring a memory for you, but it wasn't that long ago in Chapter 5 when we introduced something called the Gibbs-Helmholtz equation. And I'll scramble here as I'm talking to you to look for that page. I encourage you to look at the context at which that equation was generated, and that was generated in a section called Dependence of Gibbs Energy on Temperature and Pressure. So the Gibbs-Helmholtz energy clearly connects changes in the molar Gibbs energy to temperature, and so the form of the equation that we just expressed here is equated with the answer to the Gibbs-Helmholtz. So that's what you're seeing here. Now, the delta G in Chapter 5 didn't necessarily have to do with vaporization. For us, it's vaporization. So that's why you see the vaporization subscript added in here. So what Gibbs-Helmholtz told us is that the rate of change of Gibbs free energy, depending on temperature, is going to be connected to its enthalpy change. That's assuming some other things are constant. I think if pressure is constant, so you're kind of you don't allow for entropy to be involved here. So it's the enthalpy change. It's the enthalpy change is the source of the Gibbs free energy change. That's the half of that what I call the MCAT equation. So connecting Gibbs-Helmholtz with the equation that we just derived above yields this term, and a rearrangement gives this expression, 6.35. So this becomes the jumping off point for our goal. Our goal is to connect the concentration changes impact on the boiling point. So you see differentials here. Guess what we're going to do when we see differentials? We're going to have to integrate, and I'll do that on the next slide. So, scrambling for my notes here. To get a literal relationship between mole fraction and temperature, we need to integrate. And there's a couple of factors here. We're going to let the mole fraction of the solvent while it's in solution connect to the temperature, the new boiling point. So that's the mole fraction at the new boiling point, and the mole fraction of the pure solvent is 1 for the temperature, the boiling point temperature at TB. So we're going to basically integrate over this range, the range from the lower boiling point TB to the new boiling point TB prime. On the left-hand side of the equation, that is integrating from the mole fraction of 1 to mole fraction at TB prime. So if you do the integration, you get rid of your differentials, you're going to get a natural log of the mole fraction of 1, and then a term that has the subtraction between the two limits of integration. Now this may seem a little tricky. Notice this expression here on the bottom. One thing that I didn't show is that this actually is TB prime times TB, but the assumptions being made is that the boiling point change is so small, this is an approximation. So the term that's inside the parentheses is the result of an approximation. And so that ends up yielding this expression on the right. So that where delta T is the change in boiling point. That's the delta T. So we're going to clean this up a little bit. So really what we've done here is we have connected the mole fraction of the solvent to the change in boiling point, but we're going to make it look a little neater. Now, one of those things that you studied in calculus were power series, and you may have wondered, why am I doing this? I'll never see it again. Well, I just made a liar of that idea because I'm bringing in something called the Maclaurin series that I think I vaguely remember from calculus, in which the Maclaurin series basically takes this expression. So notice how we had the natural log of the mole fraction of the solvent, and it's been re-expressed as in terms of the solute mole fraction. That's kind of convention that colligative properties usually want to express that colligative property in terms of how much solute's being added. So that's where that 1 minus the mole fraction 2 comes in as a substitute. Here's where the Maclaurin series is impacted. If the x2 is a small number, then this power series gives you this expansion, and with the realization that really the first term is going to be the most important. Remember, this is for a very small number. So when you start squaring and cubing and quartering small numbers, they basically fall out of the mix. So I've turned this natural log term into this expression, minus the mole fraction of the solute. So now we have a new expression that I've written in blue here. So I've rearranged this so that the change in boiling point is on the left, and on the right-hand side are a jumble of terms times basically the concentration of the solute. Now, a mole fraction is not the most convenient concentration unit, and maybe some echoes of Chem 122 are coming to you now. The most common concentration unit we use for colligative properties is molality, and so that little derivation is here. How do I convert mole fraction of the solute into molality? Well, I do that for you here, and finally in blue, I get basically the boiling point elevation expression that you learned in Gen Chem. Basically, you were just handed the fact that the change in the boiling point was equal to some constant times the molality of the solute. What we've done on this 2-page derivation is derive that constant for you. The constant has an R in it. It's got the normal boiling point in it squared. It's got the molar mass of the solvent in it, and it's got the delta H of vaporization of the solvent. So there's a lot of pieces get thrown into it, but that's where the KB comes from.